SweetFeet is a mobile pressure sensing platform designed to help diabetic patients. The primary cause of hospitalization for diabetic patients is foot-related injuries. The root cause is diabetic neuropathy. Given time, high blood sugar levels can damage a diabetic patient's nerves, often in the feet. This causes them to lose feeling in the area. In an unaffected person, pain in the foot serves as a reminder to rebalance weight or not put pressure on an injured portion of one's foot. Without this feedback, sufferers of diabetic neuropathy can easily injure their feet through poor distribution of weight, or distribute more weight than they should to an already injured area. This can lead to slow-healing pressure sores on the bottom of a patient's foot, or a more serious condition known as Charcot's foot. Charcot's foot is a condition that develops over time when a patient continues to distribute their weight poorly, which causes serious damage to the bones in their feet. This can lead, in turn, to deformity that is difficult to recover from and may necessitate amputation. To analyze gait abnormalities which can lead to these conditions, researchers in the lab have a number of tools available to them, but they require the use of a dedicated room or thousands of dollars worth of equipment. To remedy this, we sought to create a new system that was mobile, affordable, and did not necessarily have to be used solely in the lab. For guidance on how we might do this, we contacted researchers at the Medical College of Georgia and the University of Arizona College of Medicine. Their feedback helped guide the design of our resulting product, the SweetFeet platform. It consists of a series of force-sensitive resistors attached to a removable shoe insole. These sensors can be placed under a series of key points in the foot, below the metatarsal heads, below the toes, and below the heel. Alternatively, the sensors may be placed wherever the patient's doctor decides they will be most beneficial, as Charcot's foot can cause irregularities on the bottom surface of a patient's foot. These sensors are then wired to an Arduino, powered by an ATmega 328 microcontroller. The sensor input is then converted to newtons by the Arduino and saved, along with a timestamp, to an onboard SD card. The Arduino and SD card, along with the battery pack to power them, are housed in an aluminum case which is attached by Velcro to an ankle brace worn by the patient. The resulting system is relatively inexpensive. It can be built for under $100. In the ideal usage scenario, a doctor would be able to lend this device to a patient. After several days, the device would then be returned to the doctor, who could analyze the data and determine if the patient has developed any dangerous gait abnormalities. In the future, we would like to aim for a more physically robust system, as well as one that is more lightweight and draws less power, as our current solution is somewhat fragile and relatively heavy, and needs to run off of a 9-volt battery for several days. Some of the difficulties we encountered in these areas were caused by the design of the Arduino itself. It is an excellent prototyping platform, but for future implementations, we will instead build a system around the ATmega 328 that it uses, and add only those permanent components that we need. Furthermore, this will decrease the cost of an already inexpensive system.